Welcome to our discussion on applications of growth and decay, which are really just applications of exponential and logarithmic functions. Now, in populations, bank accounts, radioactive decay, all these different types of things, there's always a rate of change, and we're always going to hold that constant. So the average growth rate is basically considered as a constant percent of the current value. So like it increases by 5% each year or 10% each month or, 2% each minute, depending on what you're looking at. In calculus, a growth formula or a decay formula is derived based on this idea. And this formula is presented in its most basic form as simply A equals A sub 0 e to the RT. Now you'll see this um, basic equation in countless textbooks with various different letters in these places, but they all mean the same thing. A is always the future value. It's how much you have after a certain amount of time has passed. A sub 0 is the initial value. Anything with a sub 0, anytime you see a variable sub 0, that always means the initial of whatever that is. So this is the initial amount, and this is the future amount. E is that special irrational number, E 2.71, blah, 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 blah. It's like pi, where the decimal goes on forever, it never repeats, doesn't have a pattern, blah, blah, that kind of thing. R is your rate of change. So it's how fast something is growing or decaying. It's always a decimal, but in the formula, we always put it in as sorry, it's always a percentage, and in the formula, we always put it in as a decimal. So if something is growing by 3%, R would be 0.03, right? If something was growing by 30%, it would be 0.3. That's where our students make a lot of mistakes, is remembering how to convert percentages to decimals. And then, of course, T is time. For the most part, for these standard formulas, T is always represented in years. There are applications of these formulas where T can be a different time frame, but for this general thing, we're always going to have years. Now, like I said, there are other various, let's say, versions of this formula. One of the more favorite one that you'll see is P equals P0 e to the RT. And here, instead of amount, they're using P for population, right? Same exact formula. Sometimes you'll even see where the variables are switched around and they'll have A equals PE to the RT. There's no sub-zero. And this is just A for future amount equals P starting principal e to the RT. This version of the formula is usually used when we're talking about money, right? So this is for continuously compounded interest. This one here is usually for populations of things. So it could be anything as small as populations of bacteria in a petri dish, or it could be populations of gazelle in a nature park or something. Also, obviously, populations of people. And then this one is just kind of the more generic, where we're just talking about amounts of things, which of course you could talk about amounts of gazelles, amounts of amoebas, amounts of people, right? So anything can be an amount. It can also be a population, and money is money. But you can see how all three of these are the same thing. You can come across them in any form depending on the type of book you're using. But I just want you to realize that they're all the same general formula. Okay, let's use this, right? You can use the formula as long as the units of time are the same. That is, if the time is measured in years, then the growth decay rate is in years. But if the time is measured in day, then the growth decay rate also must be a daily growth rate. So that's the one thing. So I told you that sometimes those the t is not in years. It'll be days or minutes or hours, something like that. Well, when that's the case, the growth rate, the r, has to also be measured in that same time period. So that's kind of the one little asterisk caveat that we have to have with these things. Okay, let's look at an example of population growth. So in 2009, the world population reached 7 billion. If we assume a growth rate of 1.5%, when will the population reach 8 billion? Pretty easy, straightforward question. All we have to do is, identify what all of the variables are and plug the numbers in. So if we're growing at 1.5%, we can see that r equals 0.015. Remember, as a decimal, our initial population is our a sub 0. That's 7. We'll just leave it as 7 instead of putting a, crap ton of zeros after it. We'll just do 7, and then we'll know our answer is in billions. And so then the A, right, the answer, the amount will also just be 8 instead of putting a bunch of zeros after it. And when we plug all these things into our formula, we see that we have everything except for t. So we need to solve for t. And hey, we've kind of done things like this before. We know that if we have to solve for an exponential, if we have to solve for a power, the first thing we do is we isolate that power. So divide both sides by 7 and get that base, in this case e, all by itself. Once we have that, we can take a log or a natural log or a log of whatever base we want of both sides. Because this base is e, we would take natural log of both sides because that's what undoes both sides. So you take natural log of 8.7, you take natural log of e to the stuff, and the natural log and the e's undo each other, and it's like squaring a square root. All you're left with is just the stuff, right? So that's where that's why the e just disappears, so to speak. And so the last thing, right, if we want to solve for t, is we just divide by the 0.15. And that would be our answer if we wanted to keep it precise, right? Because natural log of 8/7 is going to be one of those irrational numbers that goes on forever. So if you wanted a precise answer, this is the only way to be precise. But that doesn't tell us anything. We want to know how long it's going to take, right? If at 2009 it was 7 billion, when will it be 8 billion? And you go, oh, well, that'll happen in natural log of 8/7. And somebody goes, shut up, man. How many years is that? So you actually have to plug it into a calculator, get 8.9, right? Rounded. So this means that we should pass 8 billion in the year 2018, right? Because 8.9, so 8 and then 0.9 of a year. So somewhere kind of in that 8th year, not quite up to 9. All right, radioactive decay. Same idea, that we know that certain things decay over time. You have certain mass and it gets smaller because energy is being released. And based on that, we can figure out how old things are. That's what carbon-14 dating is all about. That's how they can figure out how old fossils are. It's based on, we know how much carbon-14 was in whatever that substance is, a mammal's bone or a certain plant life. We know how much carbon was in it when it's alive, because that's held constant. And then as soon as that organism dies, whether it's a plant or an animal or whatever, the atoms start to decay, right? So the carbon-14 stuff starts to decay, and then we can measure how much is left and solve for time and figure out how long that thing has been dead, right? So how long, how old a fossil is. So all radioactive isotopes decay at different rates. So instead of carbon-14, we can look at neptunium-239 and say that it has a decay rate of 31%. Now, we imply that the rate is negative because we say it's a decay rate. So whenever you see a decay rate, you know that your R is negative. They won't normally list the decay rate as negative, but in the formula, you have to put in a negative. So if there's 100 milligrams of 239 and it decays to 73.36 milligrams after 24 hours, find the value R in the growth decay formula. So now we're going to solve for R instead of T. Plug in everything you know. Right, the amount that you have at the end is 73.36. The amount you started with was 100. The time, right, that it took 24 hours. So we put 1, because remember it said they want us to express everything in days. Put all that stuff into the formula. We know that we have to solve for R, so we divide both sides by 100. Then we have e to the r. We undo e by taking natural log of both sides, and that's our r. Plug that into the calculator, and you get negative 0.3, blah, 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 blah. You round that, and you can see that you get 30.97, which rounds to roughly 31%. You notice there's a negative there, which tells us it's decay rate. Okay? Sometimes we like to discuss decay rates in what's called a half-life, and it's just the amount of time it takes for something to lose half of its mass. Carbon-14 has a half-life of 5,730 years. So again, that's what we can use to figure out how old things are. So if 100 milligrams of carbon-14 is present, we are given that in 5,730 years, i.e. when t equals 5730, there will be 50 milligrams present. We can use the formula, plug in all those bits and pieces, solve for r, right? Divide by 100, take natural log, divide by the constant to get r by itself, plug it in the calculator, get your approximate answer, and you can see that that is the decay rate for carbon-14. And it's a really small number, right? That e to the negative 4 in your calculator means that you're moving the decimal place 4 times in the negative direction, right? So it's going 1, 2, 3, 4. And when you do that, right, 1 and then 2, 3, 4, when you move 3 more times, that just means you're going to have 3 zeros and then 1, 2, 0, 9, 6, 8, da, 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 da. So you can see it's really, really small. It's way down here in the fourth, right? So tens, hundreds, thousands, 10,000s. That's, 1/10,000th. Really, really small r. So if you're trying to do this as a percent, remember this is still negative. Negative just tells you that it's decaying. But if we want to write this as a percent, wouldn't that be, remember you'd basically move it times 2 and it'd be it would be 0.012%. Tiny, 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 right? And negative. Okay, logarithmic scales. There are all sorts of growth and decay things that are represented well by logarithmic scales. One that we talked about in another video, seismographs, i.e. earthquakes. So the amplitude, the vertical distance between the peak or valley of a seismograph and the horizontal line that kind of goes in between the two, that's the amplitude. So when that needle is bouncing up and down, up and down, up and down because of the earth shaking, that is how we can measure the amplitude of an earthquake. So we measure it in really, really small units, micrometer, right? So you're talking about micrometers, little tiny, 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 little itty bitty measurements. In 1935, Charles Richter, seismologist, blah, 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 right, came up with kind of the formula for the amplitude. The magnitude equals log of A over A0, where A0 is the amplitude of a standard earthquake. Kind of if you think about as being the smallest kind of measurable bounce. And it's defined to be negative 1.7 for a seismograph that's located 20 kilometers from the epicenter. So that's why we have multiple seismographs all over, because based on how far they are and how much they move, based on the distance, you kind of triangulate and you can figure out where the earthquake was and how strong it was. If you just had one, you wouldn't know what direction it came from. You wouldn't know how strong it really was because you wouldn't know the distance, right? So that's why we have to have multiple seismographs all over the place, and then you use the multiple readings to figure out what's going on. So if you use the simple properties of logs, you can take, right, remember log of a quotient and make it the difference of logs. So it's log of a minus log of a sub 0. You can plug in what log of a sub 0 is, and you get the magnitude just equals log of a plus 1.7. So if the seismograph is located 300 kilometers from the epicenter, then log of a sub 0 is defined to be negative 4.0. So since the calculation of the magnitude depends on the distance, you have to know all these types of things to figure it out. And so you need to be measured at 3 different locations in order to triangulate where it comes from and how strong it was, because you have to know distance and location, right? So that's why you need 3. So here's some examples of some of the biggest earthquakes kind of ever recorded. I'm sure there have been others, but since we started recording these things way back in the early 1900s, these were kind of backwards extrapolated based on data, because we obviously in 1935, so when we came up with the scale, we really didn't have a scale then, but we could go back and based on what we know about how much stuff moved, we could give these things some magnitudes. And there are some doozies you can see, and even some bigger ones, right? Chile at 9.5. So let's look at an example. If you have a seismograph that's 300 kilometers from the epicenter of an earthquake recorded at a maximum amplitude of 4.9 times 10 to the power of 3 microns, remember that's a little, that um is the symbol for microns. Find the magnitude. What would be the Richter scale reading for a seismograph that was 20 kilometers from the epicenter at the same earthquake? All right, so first let's do the first part. We know if we're 300 kilometers away, we're adding 4.0. So you take log of the amplitude, the reading that you got on the machine, you add 4.0 to it, and you get, it roughly comes out to a 7.7. If it's 20 kilometers from the epicenter, you do the same thing, but now you're only adding 1.7. So now you get that it's a 5.4 earthquake. And so you can see that distance has a bearing, because the needle, right, the moving of the needle is basically measuring how much the Earth is moving right there at the seismograph's location. So you have to multiply that by different multipliers depending on how far away the actual magnitude occurred, or sorry, the far away the actual earthquake occurred. Okay, so why are these things logarithmic? It really comes down to the fact that we're measuring things on huge scales. You know, we're measuring huge amounts of energy, and the difference from one to the next can be so much bigger that we kind of have to decrease that so that we can understand it. Otherwise, the numbers would get too big. The idea is that if you increase a magnitude, so if you go from a 4.0 to a 5.0, that 5.0 is actually 10 times stronger. And if you increase from a 4 to a 6, it becomes 10 squared or 100 times stronger. And if you go from a 4 to a 7, that's 1,000 times stronger. So you can see why we had to kind of take logs for this scale, because otherwise the numbers just get out of hand. They get too big. Decibel rating, which measures the intensity of sounds, also uses logs for the same reason, is because the intensity levels can get so big so quick. And just like with earthquakes, distance plays a role. And so because of this, the unit of measurement for measuring sounds, called a decibel, is defined as a ratio of the intensity of one sound to another. So you'll have kind of the sound that you measure, and then you'll have this base sound, this I sub 0 sound. And it's the intensity of something that's barely audible to a human being with normal hearing. So this is supposed to be kind of the smallest, softest sound that a human with a healthy ear can hear. And the reason why we don't just put this in the formula and we leave the formula as I sub 0 is because we might want to recalibrate this equation to somebody with bad hearing, or more importantly, we might want to recalibrate it to things other than humans, you know, like dogs and bats and things that have far different hearing than humans. We define a painful sound as being 10 to the 4 or 100 trillion times more intense than a barely audible sound. And then we can, kind of come up with the standard decibel formula as being just decibel D equals 10 times log of the intensity of the sound divided by the intensity of this barely audible sound. Here are some decibel ratings just to understand, right? A whisper already has a decibel of 25. Quiet room, right? 30. Traffic, 70. A train going by, orchestra, right? There's your pain threshold. So anything above 120 starts to hurt your ears. 125. There's also thresholds for when damage occurs, and whether it's temporary damage or permanent damage also depends on how high up the intensity scale you go. Okay, the background sound of a study room was measured to be 10 to the negative 2 watts. Find the decibel rating. So that's really easy. Just plug in what you know into the equation, and solve, right? So we use 10 to the negative 10 because that's what we measured. We use 10 to the negative 16 because that's our I sub 0. Use the rules of exponents, and you can um, figure out that that's going to be 10 to the 6, right? Because remember, it's the top number, top power minus the bottom. So negative 10 minus a minus 16. So it's negative 10 plus 16, which becomes positive 6. So you're really doing 10 of log of 10 to the 6. Remember, when you do log base 10 of 10 to a power, these things just undo each other, and this just becomes a 6. So you end up getting 6 times 10, or 60. So that's a decibel of 60. Now, if you remember, 60 is right there at conversation. Okay? And that is basically everything we need to know, right? The scale, every time you go up by 10, each increase of 10 decibels is perceived as a doubling of loudness. So a sound of 70 appears to be twice as loud as 60 to us. And that's it for applications of growth and decay.